How do neuromorphic chips mimic the human brain in circuit design? Imagine a computer chip that learns, adapts, and processes information in a way that closely resembles how the human brain functions. This is the goal of neuromorphic chips, which are designed to emulate the neural architecture and activity of biological brains. To understand how they achieve this, it is essential to explore their fundamental design principles and how these differ from traditional computing systems. Neuromorphic chips are built using artificial neurons and synapses that replicate the structure and function of biological counterparts. Unlike conventional chips that rely on binary logic and separate processing units, neuromorphic systems integrate processing and memory within the same components. This integration allows for highly parallel operations, similar to how neurons in the brain work simultaneously to process information. The core of neuromorphic circuit design involves creating artificial neurons that can generate electrical signals called action potentials or spikes. These spikes are analogous to nerve impulses in biological neurons. The artificial neurons are connected through artificial synapses, which modulate the strength of the connections based on activity. This modulation is known as synaptic plasticity and is fundamental to learning and adaptation in the brain. Materials used in neuromorphic circuits often include memristors, which are resistive devices capable of retaining a state based on the history of voltage and current passed through them. Memristors serve as artificial synapses because they can adjust their resistance levels to representing different synaptic weights. This ability to change resistance in response to activity enables the circuit to learn from experience, similar to synaptic strengthening or weakening in biological systems. The circuit design also emphasizes event-driven processing, where neurons fire only when certain thresholds are reached, reducing unnecessary energy consumption. This approach mirrors how biological neurons operate efficiently, firing only when necessary to transmit information. The architecture often employs networks of interconnected artificial neurons that can perform complex tasks such as pattern recognition, sensory processing, and decision-making. Furthermore, neuromorphic chips utilize specialized hardware that supports rapid, low-power computation. This hardware often includes analog components that mimic the continuous signals of biological neurons, as well as digital elements for precise control. The combination allows for a more faithful replication of brain activity, enabling these chips to perform cognitive tasks with remarkable efficiency. In summary, neuromorphic chips mimic the human brain in circuit design by integrating artificial neurons and synapses capable of dynamic adaptation, employing materials like memristors for synaptic plasticity, and adopting event-driven architectures that conserve energy. These features collectively enable the chips to process information in a manner that closely resembles neural activity, paving the way for advanced artificial intelligence and machine learning applications.